All right, here we go with part 2 of the notes for section 10.8. When we have a situation where order is important, that's called a permutation. That's going to be a situation, say we had a math club where we needed 5 students to go to a competition. It doesn't matter what order we chose those 5 students in, they would still be the same group of 5. If, however, we were choosing one person to be a president of the club and another person to be the vice president, that would give us an actual order to it. It doesn't mean the same thing for one person to be president or to be vice president. So that's a situation where order matters. That would be a permutation. One way to find out how many outcomes are possible, again, is to list them all, but since order matters, this time there are no duplicates. So for example, in number 1, Karen is painting her bedroom. She has orange, green, blue, and purple paint. She plans to use one color as a base coat and stencil a design with another color. So an orange base coat with a green stencil is not the same as a green base coat with an orange stencil. This is not a duplicate this time because those mean different things. It would give the room an entirely different look. So we could have orange with a green stencil, orange with blue, or orange with purple. We could have green with orange, green with blue, or green with purple. We could have blue with orange, blue with green, or blue with purple. Or we could have purple with orange, purple with green, or purple with blue. Purple with blue. All right, so that gives you an idea of what that list might look like, and this time we have 12 different ways that she could do that. Alternatively, we can use the fundamental counting principle for permutation. Because we have no duplicates, you can kind of think of it this way. Here's our base, and here's our stencil. How many different options do we have for the base color? We have orange, green, blue, and purple, so that's 4 different options. But once we've chosen one of those, we're not going to use the same color to stencil with, so we now only have 3 options for stenciling, and that, not coincidentally, multiplied together gives us 12. Ingrid is stringing 3 different types of beads on a bracelet. How many ways can she use one bead of each type to string the next 3? So if we call them type A, B, and C, then she could do an A bead and then a B and then a C. Or she could do an A bead and then a C and then a B. Or B, A, C. Or B, C, A. Or she could start with C and have C, A, B or C, B, A. That would be 6 different options. And the alternative again here is to use the fundamental counting principle. She's got 3 beads that she's going to use. She has 3 options for the first bead, but now that she's used one, she's got 2 only for the second, and only 1 option left for the third. 3 times 2 times 1 gives us that same number, 6. So let's use that idea to move along here. Suppose we want to make a 5-letter password. So let's give ourselves 5 letters, or 5 spaces here. We're going to choose from the letters A, B, C, D, and E, and we do not want to repeat a letter. That means we have 5 options for our first, only 4 left for our second, 3 for our third, 2 for our fourth, and 1 remaining for our last letter. And this would be, it looks like, 120 options. If we wanted a 3-letter password from those same 5 letters and repeating is okay, then we have 5 options for our first letter, also 5 options for our second because we could repeat the first letter over, and still 5 letters for our third option, giving us a total of 125 different ways that we could do that. Now again, sometimes it would take a really long time to list them all. You could fill out your 9 blanks here for these 9 people lining up for a picture. But there is a formula for the permutations, and I'd like to take a moment to compare that formula to the formula for combinations. They are practically identical, but with one key difference, and that difference is right here, that r factorial does not exist in the permutation formula. This factor down here in the denominator is what removes the duplicates. Okay, So in this case, how many different ways can 9 people line up for a picture? So we have 9 to choose from, order matters, and we're going to use all 9 people. So that's 9 factorial over 9 minus 9 factorial, which is 0. And the convention in math is for 0 factorial to be equal to 1. So this is quite simply just 9 factorial, which is 362,880. It's quite a lot of options there. If we have a group of 8 swimmers swimming in a race that are given prizes for first, second, and third, how many different outcomes can there be if the swimmers are equally talented? Now that just means that all of them have an equal chance of coming in first, second, or third. So we have 8, order matters, and we're choosing 3. That gives us 8 factorial divided by 8 minus 3 factorial. This is 5. So we're going to leave out from 5 and below. That leaves us with 876 because the 5432 is going to cancel with this 5432. So we have 336 different ways for that to happen. Now alternatively, you could have used the fundamental counting principle as your basis for your answer here. Given that there are 8 swimmers that could possibly have come in first. Once someone has come in first, though, there are only 7 options for second place and then only 6 options for third. And it would have given you this last piece of the problem here. The last thing we're going to talk about here is how to decide whether we have a combination or a permutation. And the way that I have always remembered it is to look at the first 4 letters of each word. This may or may not help you. You can comb your hair and you can perm your hair. If you comb it, the order doesn't matter. If you perm it and you get the order wrong, you could end up with no hair. So here, order is very important, but here it is not. So we have the math club with 12 members. In how many different ways can the club president, vice president, and treasurer be chosen? The order matters because those 3 offices are not equivalent. They have different functions that they serve. So with the fundamental counting principle, we could go this way. We could say this is for president, this is for vice president, this is for treasurer. We have 12 members to choose from for here, 11 for here, 10 for here, and that is 1,320. Alternatively, we can say there are 12 math club members, order matters, so we'll use a permutation, and there are 3 positions that we're going to choose, that we're going to choose. And in that situation, we'll come over here to the calculator. And again, the NPR is on this list as well. It's just a little farther down. So we'll select that. We have 12 members to choose from, and we're choosing 3. That will give us that same 1,320 that we found using the fundamental counting principle. And number 8. In how many different ways can a team of 4 students be chosen from the math club up here for a competition? Now order no longer matters. Oops, I'm sorry, I didn't write the answer up here. This is a permutation. Down here in 8, order no longer matters because a team of 4 is a team of 4, no matter what order you chose the students in. This is a combination. So we have 12 students, and we're choosing 4 of them in no particular order. That'll be our 12 factorial over 4 factorial times 12 minus 4 factorial. Whoops, that goes out here, sorry. This would be 8. So we have 12, 11, 10, 9. The 8, 7, and so on cancel with that. And 4, 3, 2. 4 times 3 is 12. And this partly cancels there with that 10. So this is 495 different ways that we could choose a team of 4 students. If you have any questions remaining on the Section 8 concepts, please feel free to come see me in seminar and I will be happy to help you. Thanks very much.